Okay, here's a little bit more about fluids. One thing you should know about fluids is that the deeper you go, the more pressure is there. And this is pretty easy to work out. There's a little formula that you see here that has the way to calculate that. Here again, density, we're usually using rho. So if you want to switch out to that, and GH instead of D for density, either one. But as you go down, the farther down you go, that would be H, the height, or the height of the water above wherever you are. If you're right here, then you'd have all that water stacked on top of you. You'd have the weight of that water. Gravity's trying to pull the water down, and it's on top of you. So there's more and more pressure the deeper you go. And that's all you got to do. The density of the fluid times G times H. Not a whole lot to say about that. Let's say that this is a height of 6 meters that we swim down to. So if you swim to the bottom of a swimming pool, you want to know what the pressure is. You'd take the density of water, which is 1,000. Multiply that by G, 9.8 meter per second squared, and then the 6 meters, and you'd multiply that out and you'd have your number there. So nothing too fancy. I get about 58,800 for the number there. The unit should come out in pascals. Should be the regular unit of pressure. I think you can see how that's gonna play out here. If I take this kilogram and that meter per second squared, that would make me a Newton, and then this meter would cancel one of the meters here, so I'd have newtons over meters squared, and that's pascals. Okay, so that would be the best way to do it. Now that would be the number that a gauge would read right there. If I put a pressure gauge right here and look to see where the needle came to, then the gauge would read 58,800. If I put the gauge up here, then it would read 0 gauge pressure. And of course we know that outside of the water there is pressure. It's air pressure, it's atmospheric pressure. And so the gauge pressure does not include the atmospheric pressure, and we have something down here called absolute pressure that kind of adjusts for that. If you take the gauge pressure, this guy, I guess, I'm not sure what the H is, pressure at a depth, I suppose, and add atmospheric pressure, then you'd have the thing here. So if you really wanted the atmospheric pressure, we had 58,800 for the gauge pressure. I would need to come along and add atmospheric pressure, which is on average 101,300 Pascal. And so I'd have something like 159, 160, 100, there we go, Pascal. Okay, I have to adjust that up. Now there are lots of other things that you could do with gauge pressure here. Sometimes you'll see a problem. Maybe there's a water tower and there's a pipe that here's the water level like this, and a pipe comes all the way down, and you have a gauge right there. Okay, so if I had a situation like that, can you see that I'm still interested in the height of the water from here down to the gauge? It's like I swam to the bottom of a pool. It's nothing different. Maybe they might say find the height of the water if the pressure equals 200,000 Pascal, something like that. Okay, and that would be the gauge pressure. All right, so here again, pressure equals rho GH. I'm looking for H, so I'd want to divide by the rho and the G to get H. And here I want 200,000 Pascal. I'm dividing by the density of water, 1,000 kilograms per cubic meter. And I'm also dividing by 9.8 meter per second squared. And when I do this, I get something close to 20 meters here. Let's see what 200,000 divided by 1,000 divided by 9.8, 20.4 meters would be the height of that. So when you look at a water tower and it's way up there, that's why they want to store that water and then have enough pressure to push that water up a hill or through a sprinkler system or whatever it is. Have that pressure already there, and even if the power goes out, you've still got your power. Once again, this would be the gauge pressure, the 200,000, and if I need the absolute pressure, then I would have to add atmospheric pressure, 101,300, and that would give me 301,300 Pascal for the absolute pressure. Okay. Unfortunately, physics books aren't always really clear about whether they're giving you or want the gauge pressure versus the absolute pressure. So just look and see what they're asking for there. Right here, Archimedes' principle and buoyancy. This is kind of a silly picture, but the guy is displacing air. He's pushing air away, so the air is going to push back on him. Now, you can see he's not going to float above his desk here. The idea is that there is an upward push, a buoyant force we call it, and that buoyant force is easy to calculate. Simply the density of the fluid times the object's volume times g. Okay, so I'll put that over here. The buoyant force equals the density of the fluid. The picture, the guy's in air. So air has a very small density. He's going to get a very small buoyant force, not enough to hold him up. G goes in there, and we put the volume of the object in the other formula. It would be better to write the displaced volume. The displaced volume is the amount of air or liquid or whatever it is, whatever fluid is pushed away by the guy's volume. And one way to think of this buoyant force is to say, well, every action has an equal and opposite reaction. So if I throw a canoe in the water, the canoe pushes water, and by every action equal and opposite reaction, the water is going to push back, and that would be the reaction force. That upward push gives this buoyant force. Another way to say it is that an object, the deeper you go, has more pressure. So up here, his head would have one pressure, but down at the bottom he'd have a greater pressure, and that greater pressure on the bottom would give you an upward push, the buoyant force here. The other force, of course, is the weight. Gravity would love to pull this guy back down to the desk, and of course it does in real life. So let's think about a couple of these. Here we go. Let's say I throw a canoe in the water, and there's the canoe, and here's the water. I'm going to shade this area underneath the water right there, and we'll call that the displaced volume. When the canoe pushes that much water away, then the water pushes back that same amount. So it's really the weight of the water that was displaced. That's not where I want that. The buoyant force here is equal to the weight of the displaced water. But I only get to count the part of the object that's underwater. If it's the whole canoe, then you've got the whole volume. All right, but that again would be the density of the fluid times g times the displaced volume. Okay, the other formula, the other force in question here would be the weight of the canoe and the cooler and the dog and the kids and the paddles and the life jacket and then whoever's paddling it, whatever else. You put all that weight pulling down. You can see there's two forces here. So you'd say the sum of the forces is equal to mass times acceleration, but we're hoping that the canoe does not accelerate down, that it doesn't sink. We want to put it there and keep it static, so we set that equal to 0. I'd have the buoyant force upward, and the weight down would look like that. The buoyant force here, we can fill that in, the density of the fluid times g times the displaced volume. and then minus mg equals 0. And typically they'll give you some numbers and expect you to find something else. For example, here, let's say we wanted to find the displaced volume of the canoe. So maybe the problem reads I don't know, 300 Newton canoe. Well, let's just put kilograms here. 300 kilogram canoe, and that's all the gear and people and everything. Is in the water, and I'll put fresh water here. If you were in seawater, you'd have a slightly different density, so it would change things. You'd need to look up the density of seawater. Is in fresh water. Find the displaced volume. You can see that this is pretty easy stuff, right? Move the mg over to the other side. I've got a g on the right and a g on the left. Those will cancel out, divide by the displaced volume. And here I'd have 300 kilograms divided by the density of the fluid, which is 1,000 kilograms per cubic meter, and that would be 0.3 cubic meters of water that you would that you'd have to displace there. The canoe would sink down until it had displaced 0.3 cubic meters. I like to design and build boats, and this is a problem that I work quite a bit. You know, how big of a boat do you have to have if you want to put 6 people and this much stuff? And there's actually some neat software. If you're interested in that kind of thing, come and talk to me and I'll show you. There's one other kind of buoyancy problem that we can do. Maybe there's a line on it. Maybe I've got a concrete block under the water here, and I've got a rope on it. We'll call that T. I get a little bit of help from the buoyant force. The block is displacing water, and here notice that the displaced volume is the total volume, right? The whole thing is underwater, so all of that counts for the volume, whereas on the canoe it was only the part that's underwater. Here it's all underwater. So when I build this equation, sum of the forces equals mass times acceleration, but we want the acceleration to be 0. Here I have 3 forces, T plus F sub B minus mg equals 0, like that. And I'd fill in the here's the tension. Fill in the buoyant force. And again, they would give me all of the numbers except for one, and I'd solve for that. Sometimes it seems like there's not enough information. Okay, if you had a problem that said a concrete block, and then maybe they tell you the density of concrete, or you can look it up if it's a homework problem or something. Let's say, I don't know the density of concrete. Let's say it's 6,000 kilograms per cubic meter. If I had a block of concrete 1 meter by 1 meter by 1 meter, might weigh about 6,000 kilograms, something like that. Here maybe it measures 0.2 meters by 0.1 meter by 0.1 meter. Okay, and then this thing is submerged. It's I can't get it going today. Submerged in water, and we would like to find the tension in the rope. How hard do we have to hold that thing up? Now obviously if it's not in the water, we have to hold the whole weight of the block, but here I'm getting a little bit of help from the buoyant force. So when I look at my variables over here, that's what I'm looking for. I know the density of water, I know G, I can find the displaced volume right there. I know G, and here I can't cancel G out because I don't have it in that first term in the T, but I don't know the mass of the block. So there's seemingly two unknowns here, and I can't solve that one equation with two unknowns. So whenever you run into a situation like this, there's a little trick. You say, let's think about the block. And for the block, the density of the block is equal to the mass of the block divided by the volume of the block. And that would be the entire volume of the block, even if it weren't completely underwater, right? We're thinking about the block here, above water, underwater, doesn't matter. Just that would be the density of the block. So see how I can say density of the block times the volume of the block would be the mass of the block. So right here, all I have to do is come along and say, well, I've got something that is 6,000 kilograms per cubic meter, and I want to multiply that by the dimensions, 0.2 times 0.1 times 0.1, and I've got myself a 12 kilogram block here for the mass of the block. So sometimes you have to do that and then take that number and drop it in right there. This is your get out of jail free card right there. When you seem to get stuck, go back to the density formula and think about the object itself. And I think you can see where that's going right there. We're not really interested in the number, but the idea is that, well, phooey, let's get the number here. I'll go ahead and put everything on the other side. I'm adding 12 kilograms times 9.8, add that to both sides, and then I want to subtract the effect of the buoyant force, so that'd be minus 1,000 times 9.8 times 0.2 times 0.1 times 0.1, and I'd get about 98 newtons. Okay, for the tension that I have to hold up. If it weren't underwater, let's say I'm pulling this block at constant velocity up to the surface, as soon as I get it out of the water, then I'd have to hold the whole weight, right? So T would be equal to mg. That'd be 120 times 9.8 would be 117, almost 118 newtons. So that buoyant force has given me about 20 newtons of help. It doesn't feel as heavy when it's under the water as it would out of the water right there. Okay, but those are the only two kinds of buoyant problems that I expect you to see. One has three forces on it, the string and the buoyant force and the weight. If you don't have the string on there, like a canoe problem, you know, then you've only got two forces, the buoyant force and the weight there. All right, set up the force equation, see what you get. Right here is a hydraulic problem, and let's run through this real quick. You can see here is a floor jack. I've got one of these at home, this thing right here, and I can slip this under my car and I can pick up my car with one hand. I'm just amazing, aren't I? Actually, what that thing does is it multiplies my force. So if I push down with 50 newtons, it might pick up 200 newtons or 2,000 newtons. It depends on how the thing's made. Down here at the bottom, you see a dump truck, right? And you've seen these hydraulic cylinders. It's the same thing that's pushing up right here on the floor jack. Incredible multiplication of force here. Let's talk about how that works. Basically, I'm going to have some kind of block, some kind of material here, and there will be a little hole and a big hole. Okay, I could take a block of steel or plastic or wood, drill a little hole, drill a big hole, connect them with this tunnel right here. And what I want to do is to fill that thing up with fluid. So I've got typically it's hydraulic fluid, a type of oil that fills that stuff. Then put a piston up here at the top of this one, and usually there's a plunger, some kind of rod, you know, that pushes up and stuff. Here's the one over here with a rod coming up out of that. And so that's the scenario. The oil can't slip past those pistons. There's an O-ring or something to hold it, all the fluid in there. And I'm going to push down with a little bit of force on this side, and it pushes up with a big force on that side. How does that happen? Well, what happens is this is fluid down in here. So if I pick a point here and call that point 1, and pick a point over here and call that point 2, the pressure has to be the same at those 2 points. P1 has to be equal to P2. The argument there would be this is fluid. If I had high pressure on the left and low pressure on the other side, then some of that fluid would move and it would equalize, it would balance out so that the pressures were the same. If it weren't, if that didn't happen, you might walk into a room one day and all the air be up in the corner of the room, right? And there's no air anywhere else in the room. Well, that doesn't happen. I've never seen it happen. So we feel pretty comfortable saying that's not liable to happen. Right here, pressure is nothing but force over area. So F1 over A1 would be pressure 1. Force 2 over area 2 would be pressure 2. And I've got myself a really nice little simple formula. It's a proportion. And I look at the cross-sectional areas of these tubes right there. This versus that is what makes the difference. When I have a little cylinder and a bigger cylinder, put a little force on the little cylinder, you get a big force on the big cylinder. Let's just make up some numbers here. Let's say that A1 is 6 square centimeters. A2 is, let's go with 60 square centimeters. All right. So if I push down with a force of 50 newtons here, and I'd like to know what F2 is, we'll solve this thing for F2 here. And I'd put in my numbers. I'm pushing down with 50 newtons. A2 is 60 centimeters squared. A1 was 6 centimeters squared. The centimeters squared cancel out. 6 would go into 60 10 times. 10 times 50 would be 500 newtons. If I push down 50 newtons on one side, I get an upward force of 500 newtons on the other side. That's how you can lift a car with one hand. That's how you can dump out 40 tons of rock out of that dump truck with that little rod. You get that incredible multiplication of force there. Now, there is one other thing that we probably should, one other formula here that you can do. I don't get that multiplication of force for free. I don't get anything for free, right? So what happens here is if I push that piston on the left down this much, right? If I push it from where it was down here to this new spot, that would mean all of this fluid got displaced. That fluid had to go to the other side, and that's going to push up on the other side. So switching colors here, that would move this one up. But if I spread this much fluid over a bigger plate, it's going to be a much smaller distance. Let's call the distance that this one goes down L1, and let's call the distance that this one goes up L2, like that. The argument goes like this. Those volumes have to be the same. So I would write that the volume on side 1 equals the volume on side 2, and that volume would simply be the cross-sectional area times the distance that it moves, and I'd get that on the other side. Okay? So right there I have a relationship, and you can see, remember that factor of 10 that we had there? If I push side 1 down 10 centimeters, the other one only goes up 1 centimeter. That's why on my floor jack I have to stand there and pump the handle back and forth in order to get the whole car up far enough to get under it or something. Okay, so that's hydraulics. You've got these two little formulas, and you can work with that. That's pretty straightforward. Next up, well, here are those formulas again, and I suppose we could do another example of that, but let's save it for class, see what else we have here. This is fluid flow, and whenever you have fluid moving in a pipe, there is a certain velocity of that fluid. V1 is what they've called it here. Notice that these are little v's for velocity, whereas the others were big V's for volume. All right, that's a little bit unfortunate, but that's the way it goes. I don't know what's going on with the red arrows here, but let's say this pipe chokes down. The velocity's got to speed up on that side. If I'm moving a certain amount of water through here, and we call that the rate of flow. So R1, the rate of flow, that's got to be the same at these 2 points, right? Whatever water I push into one side of the pipe's got to come out the other side of the pipe. Water is incompressible. There's no little magic room to store it in. Whatever goes in one side comes out the other side. So R1 has to equal R2. That rate would be the cross-sectional area A1 times the velocity V1, and same thing on the other side. You can see here that this would be fine to work with right there if you wanted to calculate the areas and plug them in. Or you could say, typically they give you the diameter of the pipe. Maybe the diameter here is 6 centimeters, and the diameter over here is 1 centimeter. Okay, so if that's the case, maybe you want to say, well, area 1 is pi diameter squared over 4, or pi r squared would work too. But here we're working with the diameters. The pi's would cancel on either side, the 4's cancel, and I end up with this thing. That might be a nice alternate way. Either one of these works fine. But if I know the velocity in the first side of the pipe is 3 meters per second, then pretty easy to come along and calculate the velocity on the second side. I would simply have 3 meters per second times diameter 1 was 6 centimeters, and then down here I'd have 1 centimeter, and that gets squared. 6 squared is 36 times 3, I believe, is 108. So you can see that speeds up quite a bit there. Went from 3 meters per second to a big number, 108 meters per second. So when you choke the pipe down, the water's got to speed up to get that same amount of water through a skinnier pipe. You've done this before. You go out in the yard and you take the garden hose and you put your thumb over the garden hose, and the water goes faster and farther, right? You're just choking back the volume or the cross-sectional area, and the fluid flow, it's got to be the same, but the velocity goes way up, right? So we've seen that kind of thing. Here's the other equation that deals with water moving in a pipe. Maybe the pipe size changes, like you see here, and the thing goes up. Okay? When I do that, I've got an equation here, big, long, scary thing, but it's not really that bad, called Bernoulli's equation. Bernoulli's equation tells me everything that I want to know about this point and this point, point 1 and point 2. And there are a number of variables that we would be interested in there. I guess that's actually pressure 1 and pressure 2 that I just circled. But we are interested in the pressure and the height of the pipe, or at least the relative height, and the velocity, like that. And then those same variables at the other side. And so you can see there's, this is exactly the same as that, except for the subscripts. So it's just saying whatever's going on right here, it's got to be the same as what's going on right there. This is really a conservation of energy problem. Remember back in that chapter where we said the potential energy plus the kinetic energy had to be the same at both points? Well, this is very similar. Density is really mass over volume, right? See how I could just kind of replace that temporarily with an M and an M, and then I'd have, this much of it right there. mgh would be the potential energy. 1/2 mv squared would be the kinetic energy, and I've got it over here at point 2 as well. All I'm really doing to conservation of energy is adding that pressure. The pressure it's a kind of energy that pushes the fluid up, so it makes sense that that's got to go in there too. All right, and I'm going to erase all that mess. But that's Bernoulli's equation. We'll try one of these here, maybe even using the other thing. So let's say that I have a 15 centimeter diameter pipe at the ground level, delivers water at 3 meters per second. Water goes up to the 4th or the 16th story, whatever you want. Water goes up, pick a number here, 30 meters, and into a 1 centimeter pipe. That'd be about a 1/2 inch pipe, which is what we use upstairs. We need a certain pressure up on the 16th floor, or whatever it is. Let's say that number is 200,000 Pascal. I think it's actually closer to 240. Let's go with 240,000 Pascal. That's about 35 psi, which is what city water pressure's typically set at. So at the top, and so the question would be, how much pressure do I need at the bottom? Find pressure at the bottom. Okay, this is the way you'd have to build buildings, right? Pressure at the bottom. The picture would look something like this. I'd have a big pipe down here, the pipe that brings the water to the building, and then it goes up, 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 and it's a little bitty pipe up there. So I've got something that looks like that, and we're interested in all of those variables. P1 is what we're looking for. P2 needs to be 240,000 Pascal. In order for the sprinklers to work, in order for the water fountain to do that little arc and you can drink out of it, and in order for the toilets to fill fast enough, wash your hands, whatever. Pressure 1, we've got the diameters here. Diameter 1 was 15 centimeters. Diameter 2 was 1 centimeter. Velocity 2, we don't know that one yet. Velocity 1 was 3 meters per second. And what else do we need? Height 1 and height 2. You could call anywhere you want 0. The thing that's easiest and makes the most sense is say, well, this is down at ground level, so I'm going to call H1 0. And then up here, it goes 30 meters up, so H2 equals 30 meters. That's the easiest way to do it because you lose a term that way. Let's go ahead and write down Bernoulli's equation. Pressure 1 plus the density times GH1 plus 1/2 density V1 squared equals pressure 2 plus density GH2 plus 1/2 density V2 squared. See how if I go ahead and let one of them be 0, that term goes away. Makes it a little bit easier, a little bit nicer. All right. In all honesty, it doesn't matter how you do it. You could pick 0 to be somewhere else. Maybe this one's really 30 meters in the air, and then 30 meters above that would be 60 meters. It's really the distance, the difference between those two that we're interested in. So I'd call one of them 0 if you can, just to make the math a little bit easier. Anyway, what we're looking for is P1. So I need to move this guy to the other side, and that would give me P2 plus rho GH2 plus 1/2 rho V2 squared minus 1/2 rho V1 squared. And you can see this is a lot like the conservation of energy problems. Just set everything, whatever's happening at point 1 down here equal to whatever's happening at point 2 up there. You always want to pick those 2 points and get that going. Here's 240,000 Pascal for P2. For water, I'd have a density of 1,000 kilograms per cubic meter. If this were pancake syrup or paint or some concrete that you're pumping up there, then you'd have to use its density, and that would make things a lot harder. H2 was 30 meters. To that I need to add 1/2 times 1,000 kilograms per cubic meter. We've done this one and this one. We're working on the third term now. V2 up. We haven't found V2 yet. We didn't do that. So we got to find the velocity up at the top. Remember, this is where that equation of continuity comes in. I don't think I told you the name before. But that was that A1V1 equals A2V2. That was the only thing, the other equation that we had. So we're going to have to use that here. And I don't have A1. I could either calculate A1 and calculate A2 from the diameters, which I do have, or I could switch over and use that pi diameter 1 squared divided by 4, remember that thing, times V1 equals pi diameter 2 squared divided by 4, V2, and the 4's cancel and the pi's cancel like that. So as long as I remember to square the diameters or square the radii, if those are given, then I'm okay. It's got to work out to square units. I was looking for V2, wasn't I? So here I need to take D1 squared divided by D2 squared times V1, and I have those numbers. That was what? 15 squared divided by 1 squared times 3, and so that'd be 225 times 3 is 675 meters per second there. Okay, and if I put that in here again, this is only assuming that there's one faucet open at a time, and that well, whatever, minus the 1/2 times 1,000 kilogram meter cubed, and we're moving at 3 meters per second squared right there. And I punched this thing up, and then I could go get a pump that was that big. You do need to watch the units very closely here, make sure that everything's in the same unit. We had Pascal in the first one. They all have to work out to Pascal, and you can see that they will here. This is going to be a big number with that velocity. I might have picked some bad numbers here somewhere along the way. Yeah, I get a really big number here. Okay, something like that. Now, it's not as bad as it looks, because remember, a Pascal is a whole lot of, it's a very small unit, and it doesn't, you know, I wouldn't have that kind of velocity coming out here. But I need a big pump to get water up in a tall building. It's just not going to flow up there at low pressure. You got to push it up there. Okay. Two more little things here that I wanted to mention. Torricelli's theorem. If I had water at a pressure, at a depth here, and a hole got punched in the tank, water would flow out at a certain velocity. This formula would give you that. You can actually cook that up from Bernoulli's equation. If I write out Bernoulli's equation, I need to pick 2 points, like we said we always do. But here is that equation. What do I want? V2 squared. So what I'm going to do is to pick 2 points. 1 point will be right here, and 1 point will be right there. When I look at these 2 points, they are level, so H1 equals H2, and I can just cancel that term right there. Furthermore, we make a little bit of simplifying assumptions here. We say this water is not really moving. It's in the tank, but it hasn't gotten up to the port yet to where it can come out. So V1 is 0. That one goes away like that. Furthermore, over here, P2, the gauge pressure on this thing is 0, right? There's no water stacked on top of it, so I wouldn't have anything like that. And this pressure at a depth, P1, would be rho GH like that. And so over here I have 1/2 rho V2 squared. The rho's cancel out. I multiply by 2. That would give me V2 squared. And so V2 would be equal to the square root of 2GH, which is what we had up there. It's a theorem because we can prove it using the Bernoulli equation, which goes straight back to conservation of energy. Okay, so you can find the velocity of fluid coming out of a tank if you know simply the height of the fluid above it. In that picture way back there, where we started all this stuff, there was a tube that had a lot of holes in it. Oh man. Right here, and you can see that at different heights the water is coming out faster, right? If you fill up a tube, you could take a soda bottle and punch some holes in it. Right here the water is coming out really slow. Here it's coming out a little bit faster. You can see that because the arc is more straight. It doesn't just fall off. Down at the bottom, that water's coming out pretty fast, and as evidenced by the arc there. So that's kind of a interesting thing that you can do with a soda bottle or something. Piece of pipe, fill it up with water. All right. The last little thing here that I wanted to show you then refers to viscosity, and this is Poiseuille's law. If I'm pushing fluid through a pipe, there's a type of friction. It's not really friction, but if viscosity, let's say I'm pushing paint through the pipe instead of water. Paint's kind of sticky, right? Paint's kind of, or pancake syrup. It kind of doesn't flow as well. And you know that if you take a thing of pancake syrup on a cold morning, it's really hard to get out. You stick it in the microwave for a little bit, it warms it up, it flows a lot better. The scientific way to say that would be is that the viscosity goes down. And so this viscosity, eta, the Greek letter eta here is that viscosity, that's going to affect how much resistance there is to, or how much flow there is. When I get a bigger viscosity, divide by that bigger number, it's going to slow my flow rate down. And so there's a formula there for that. We're not going to do a whole lot with it, but I wanted you to see it. The other number that sometimes pops up in fluid dynamics that you should have at least seen somewhere is Reynolds number. Here I have a pipe, and fluid is flowing through that pipe, and the question is it churning around in the pipe, or is it just flowing nice and smooth? So here I have a little formula called Reynolds number, and you can see that the density of the fluid and the velocity of the fluid and the pipe diameter and the viscosity of the fluid are all in there. So you put those four numbers in and turn the crank. If that number is less than 2100, we say it's laminar flow. A small Reynolds number means that you have nice, smooth flowing water. If it's a big number, then you have turbulent flow. It's all churned up and rolling about. You could imagine going to the river. If you throw a inner tube or a canoe into the Saluda River here, this all flows nice and smooth when the water's wide and there aren't any rocks, and everything just flows along nice and easy. When the water gets to moving fast, when the velocity goes up, when there's rocks in the way, that would kind of be maybe a viscosity kind of thing. As stuff happens, it gets very turbulent, and it changes. So there's Reynolds number again. Kind of put that on second tier of importance, as well as that viscosity thing in the last one that I showed you. But wanted you to see it, and that wraps things up. Thank you very much. Have a good day.